So the first presenter will be Dr. Jared Hutchinson, is a professor at
University of Illinois. Yeah, thank you. So I'm happy to be kicking off this little session on biotech and ag. So my hope is that I can kind of contextualize why is biotechnology important, and one reason is because it is a factor behind yield growth, which is something that obviously weighs on policymakers' minds. So the purpose of this project is to be looking at soybean yield trial data and trying to characterize something about productivity growth from genetic improvement. And this is joint work with my co-author, Scott Irwin, who happens to be here. So all the hard questions give to him. All right, so a main motivating factor, I think, is that can we keep soybean yield growing, right? So it is obviously in this graph, this is from Scott and Todd Hubbs had a Farm Doc Daily about this, trying to model growth rates in soybean yields. So we would very much like to know, is it going to keep improving? Is it going to keep going up? And so just some reasons in case you're not familiar with the importance of soybeans. It is an active ingredient in food products. So it is the oil is used in a lot of it's obviously a cattle feed. Increasingly, it's also an ingredient in biodiesel. So there's actually a food versus fuel debate we might see in the future. And so we're very much concerned about, can we keep yield improving? Can we keep it growing up? And as you can see, this is actually a quadratic function that they fit. So there is a little bit of an increase. But we wonder, right, this was up until I think about 2016. So what about now? So what we will focus on is, of the levers that increase soybean yield in this country, we're going to think about genetic improvement in particular. And we're going to get into basically a very unique data set, or at least a unique type of experiment station trial that had planted a public sector variety every single year in these locations, which actually helps us actually have a comparison over which to see how much yield improvement is happening by the private sector, right, by submitting their private varieties. So I'll get more into what the mechanics of that is. So the answer is that using Illinois yield trial data, we estimate a linear growth rate of 30 to 40 kilograms per hectare. So in imperial units, that's about a half a bushel acre improvement per year. And that's from 1995 to 2020. So one immediate contribution here is that we're the first to chart genetic improvement after 2010. And we were very happy to see that this number is not so crazy. It's comparable to what are called heritage studies, which I'll explain. But we also had some other results that this literature has not found, which is one is that GE only increased yields in one type of soybeans, which was early maturing soybeans. And then we are detecting what is a possible slowdown in genetic improvement in 2009 to 2014. And that'll be pretty obvious, I think, in the graphs I showed. So I mentioned heritage study. What is a heritage study? So I think there are two sources of literature that are very important to this topic. And this is in essence the plant science and agronomy literature. So when they want to chart genetic improvement over the past 20 years, what they do is they take varieties from all of those different years. Then they take them and they plant them in one experiment plot. They measure the yield. And in essence, they compare the yield of that variety to the year of its release, right? So this is the idea. So how are soybeans in 1995 compared to soybeans 5 years later? And in essence, econometrically, all they're doing is a time trend, right? And they're using year of release. So the results there, this is Rinker et al. 2014. This is a recent heritage study, found that this is 1968 to 2008. We saw about 30 kilograms per hectare, 0.45 bushels per acre. I want you to hold the 30 number in your mind because it's going to be important for comparing our results. All right, now on the other side, in economist land, what we're often trying to do is we are trying to quantify the impact of GE adoption on yields, often using county level data. Some of you might be familiar, there's a NASS survey that looks at percentage adoption of GE seeds. So there was a recent study, Shu et al. 2016, that found 30 kilograms per hectare. So it actually agrees with these heritage studies, but this kind of has part of the literature on GE is that it has mixed impacts, right? So here they found that GE has a null or even negative effect for soybeans. They blame this on yield drag. But then there are other studies that say there are confounding factors here. There's weather, there's management, and that's preventing the effect of GE from appearing in the study. Okay, so here's how we're contributing, is that here's an issue with the heritage studies, is that heritage studies may be picking only winners. So what do I mean by this? What I mean by this is in a given year, when a private sector is producing varieties, some of them are going to do well, some of them are not going to do well. The ones that don't do well are not going to go to market. They are not then going to appear in a heritage study 20 years later. So I feel like what might be happening with heritage studies is that you are basically getting the upper hall of genetic improvement, but you're missing some of this noise. And I think as economists who want to study innovation and understand these patterns, we need to understand the messy process of innovation. So it would be nice if we had a data set that had more than just some of these ex post varieties they're selecting. So the solution our data grants is that we have between 300 to 700 varieties submitted each year, and there's about 9,500 total. And this is including ones that never went to market, actually, never even became patented. So we have a much different view of genetic improvement than these ex post selection studies are going to have. Now, on the observational side, right, as economists, we know what can people throw in your face with a GE adoption study? It's endogenous, there's management, there's weather, there's confounding factors. So of course, these studies always kind of focus on this kind of thing. So the solution here, though, is that we're actually leveraging the experimental part of this, which is that within a given plot, management is completely constant. The only thing that needs to be sort of controlled for is weather. And we'll talk about how we do that. But I also want to point out, we actually have both GE and conventional seed in each year. And this is even when in Illinois, we have 90% adoption of GE seed. So I also think there's some heterogeneity in conventional seeds that will be handy in trying to understand the impact of GE, because we actually have some conventional seeds over which to compare. All right, so I have one slide of theoretical framework to kind of explain how we're going to solve maybe the problem you're thinking, which is, okay, but how are you going to confound genetic improvement from weather? So let's first assume that the yield of variety J at location I and time t is determined linearly by these factors. So you have Y, which is the yield, and let's call the parameter of interest beta J. So the beta is our interest. And this is the contribution of genetics. It's the contribution that J alone is giving to yield. But how do we disentangle this from the effect of location I? So that would be soil characteristics, permanent characteristics of where it is planted. And then, of course, things that happen at I at time t, which is weather, right? Or any other kind of shock. So the solution in this case is that if there were a base variety, and I just mean something we're going to call J equals 0, and it was planted at every I and also at every t, right? So if you had this variety, then you would basically have alpha I, gamma IT, and then beta 0. So then take the difference between these, and all you're really left with is beta J minus beta 0 plus this compound error term. So if you believe that we can control for this compound error term, after differencing it, right, you are going to have a pure genetic effect. So to simplify this, all I'm basically saying is that if in each year there is a variety, and it's in this case a public sector variety, and it's planted at every location I and every T, you can compare each year's submissions to that, and you can make the comparison between years because you're comparing against a genetic source that never changes compared with the market that's always improving. So that's kind of the intuition behind what's happening here. All right, so that leads to a very simple empirical model we have here, which is that we have delta YIJT. So remember, that's the difference between a private variety, this is the private sector submitting a variety, and the base variety in the same I and T. So then you're going to get just a linear time trend. That's what we've done so far here. And so this is just measuring the average growth from seed genetics linearly over time. So obviously you can expand this to nonlinear, and we're in the process of doing that. So if you into genetics, you might have heard the phrase genotype by environment interactions. And so what this is that one type of genetics is planted in a certain soil, and then it's going to react differently than, say, another set of genetics. So this technically would manifest right here in delta mu, right? So this is these other order effects that are not linear. You basically have some nonlinear impacts. So to control for that, we're going to have some controls like height of the plant, the week that it matures, the lodging score, and then some company fixed effects and then location fixed effects. So if we think that some of these, this is our attempt at trying to get at those genotype by environment interactions. All right, so let me explain a little bit about the data in case you're not familiar with the State Ag Experiment Station and how it has a role in providing information to farmers because of participation in the seed companies. So what seed companies do each year is they have the opportunity to go to the University of Illinois soybean variety trials and pay to have their variety grown at all of these different locations in Illinois. They have to pay, in 1995, it was $65 a submission, and then in 2020, it was $90. So they pay a fee, they get it grown all over the state. And then there is a report that comes out and farmers get to read this report and it compares. So for example, Pioneer has a new variety. It compares Pioneer's variety with the other companies that submitted that year and also some public sector varieties that have been in use a long time. In our case, we have Jack and Dwight and Williams. These are all 3 public varieties. And they were grown basically every year between 1995 and 2020. And so we are going to use this as the point of comparison. This is our J = 0, our base genetics over which we're going to difference in. So for all maturity group 2 soybeans, that means they mature a little bit earlier. We're going to compare them to Jack and Dwight. So that's the difference we're going to take. And then for maturity group 3, we're going to take Williams. So when I list on the graphs Jack and Dwight and Williams, I'm talking about different ways to difference the private sector variety yields. All right, so this is one feature of the data that's kind of interesting, is that company participation is declining after 2004. So this is a whole can of worms that I'm very interested in because I like institutions and I like information goods. And this is a case in which the companies are actually no longer supplying this information good the same way they used to be. So the number of companies and varieties in the data declines after 2004. And if I were to show you patent trends for soybean varieties, it would be going up in this period. So it's not as if the whole market is shrinking. That being said, companies is going down because there's consolidation in the seed industry. So that actually kind of makes sense. But number of varieties is actually going up. So that suggests there's actually attrition happening in this sample. All right, so I'm going to show you some results tables from what we've done so far. I'm first going to show you some linear trends and then some nonlinear trends. We're going to estimate a linear time trend using these 3 base varieties. So we're going to take all the maturity group 2 varieties that private companies are submitting, and we're going to subtract Jack and also Dwight to see how they compare. But for maturity group 3, we'll just have Williams to use as our base. So we have different bases over which to calculate genetic improvement. So because we have heterogeneity in genetic engineered varieties, we also are going to include a GE interaction, and this essentially tests whether GE seed varieties grew at faster rates. Do they have a statistically different time trend for genetic improvement? And then, because I talked about this attrition problem, we're going to have a robustness check where we only include companies with constant participation. So we're going to look at some of those that participated the entire time. That's kind of forcefully balancing the panel in a way. And so we're going to try to see, is that time trend completely different? Because then what if the ones that are dropping out are actually the ones driving the results? And then finally, this is kind of a preliminary part of our analysis, but we're doing some experimenting with structural breaks in the data. So we did a chow test and found 2008 and 2015. And then I'm seeing a nonlinear model that finds a slowdown in growth from 2009 to 2014. Okay, so here's a graph that you can actually see that growth pretty well. So this is yield gains over time. So blue is going to be maturity group 2, and then Williams is going to be maturity group 3, and that's that red line is maturity group 3. So what I want to draw your attention to here is that up to 2010, they all grow at about the same rate, right? You don't really see much divergence. But there is a slowdown, not just in maturity group 3, but also in maturity group 2, because it rises for a little bit and then it flattens out for a little bit. And just to be clear, this is the 5-year average. So you're probably getting some negative shocks in this period and they start slowing growth. And then we see it accelerate back. And then just for a reference point, the dotted line is the state average yield. Yes?
This is the difference between each variety of Jack. It's not the yield of Jack.
Correct. Yeah, sorry. I am going to have to reform this in the future, but this is private sector varieties and we're using different points of comparison. So really red maturity group 3 genetic improvement, blue maturity group 2. All right. So here's our estimates of genetic improvement. And I did want to show you what happens if you do not adjust them. So what if we didn't subtract a base variety? That includes all these confounding factors, weather, soil. So it turns out when you do that, you get an estimate of 30 to 40. I think Jack is the most aggressive in terms of showing genetic improvement. And there's some reasons because Jack has a huge decline. So the gap looks really big. So if I had to sort of choose one, I would choose this conservative estimate of 32. But notice if we hadn't adjusted it, it would have been 50 kilograms per hectare a year. And that's a lot larger, right? So if we hadn't dealt with these confounding factors, yield growth would have looked higher due to genetic improvement, right? So in essence, we probably had something like favorable weather during this period that's pushing yields up and making them look bigger. And then for maturity group 3, you're seeing a similar thing. You'd almost see it double, right? If it were not adjusted. All right, so here's our GE interaction. So this is the statistical test in essence of if this coefficient is significant, then GE is growing at a different rate than the other time trend. And we see for maturity group 2, this is the case and it contributes to maybe roughly half of the linear trend, but not for maturity group 3. So what's interesting to contextualize these results is that we do know from the literature that the evidence that GE itself is increasing yields is a little bit mixed, right? Because some studies will find yes, some studies will find no. So what I think is interesting is that in this study, we see it, but it's mostly due to maturity group, which either has to do with who is submitting in that group, or it has to do with, basically where companies are deciding to genetically improve, if we think this is accurately measuring that. And what's interesting here is I think in this trial, you have a lot more conventional seeds than you would have ordinarily. And there's a whole can of worms about this, which is that it's possible that seed companies take their best germplasm and put it into GE. So it's not necessarily just the trait that's improving yield, but it's also that there's the best germplasm. So, but that's neither here nor there. So when we do the attrition, we don't see the trend change really. So these standard errors are big enough that if you were to do kind of a formal test, like a Hausman test or something like that, you wouldn't find any statistical differences. So for the companies that stay participating, the trends look roughly the same. All right, so here's the one this is kind of the first attempt at this. It looks a little wonky here, but this is the added impact of 2009 to 2014 to this base trend here. And this is the added impact of 2015 to 2020. So this is how it recovered. This is what happened in the middle. And so what I want to point out is that for the Williams and Jack, maturity group 2 and maturity group 3, you're actually seeing a slowdown in growth at this period. So if you're thinking about what this model basically is think about a linear trend, but it's segmented. So I'm drawing 3 different linear trends right through the data. And so when you do that, you are finding some nonlinear impacts in this little period here. And then you do see for maturity group 2, the yield genetic improvement sort of recovers, but not as much for maturity group 3. So if we go back to this, right, you can see maturity group 2 grows. Maturity group 3 is growing at a slower rate. And these are all normalized to one period, right? So relative to where it was, maturity group 2 is higher. All right, so that's all I have. So I'll just wrap up with some concluding remarks and maybe we have some questions or discussion. So during this period, confounding factors would have made yields appear 50% larger, which is really interesting because we know that weather is going to confound the impact of genetic technology. And so in our case, we've actually seen in this period, it's pushing yields up, makes them look too big. We found a linear growth rate about 0.5 bushel per acre a year, and that's in line with these recent heritage studies where they plant all the varieties at once and look at the year of release. And then we see some mixed evidence about GE varieties making a significant contribution to yields for soybeans in maturity group 2, but not maturity group 3. So it seems like there's mixed evidence based on the maturity group. And then we're still in the process, but of trying to detect whether there is this slowdown in genetic improvement. And if there is, the next question is why? What was happening during that period, right? What might have been happening with R&D or companies or to what extent is this driven by people participating or not participating at the University of Illinois public variety trials? So let me leave it there. And I think probably have some time to take some questions. So thank you. Yeah. Yeah, so in this case, CD management should be the same across plots because it was a yield trial, just to be clear. That's a good question. I think, so hopefully it might have been different, but hopefully what happens is that within location I, it is the same seeding rate. So you should have the same comparison, but that's a good point. I'll have to check on that. And because it's kind of in the details of the trial information that says we use this seeding rate.
And I know seeding rates aren't really yield, so I think that they are important. But
Right, okay.
That there could be other factors too, like herbicide use or row width or.
Right. Row width I know is the same over the whole trial because they there was one narrow trial they did in Urbana, but we're not including that. So definitely I know row width. I definitely know that herbicide has changed though. So that is something that I should look into about that. Yeah. Oh man. Yeah. I did. Okay, so I had, what was that? The question was about yield variance and what's happening over time. I've been showing averages, right? So the beta J is going to measure like average linear growth. Oh, such an interesting question. So I did a bunch of actually like first order stochastic dominances of these private yield distributions. So if you treat every company's submission as a draw from that distribution, what I actually see is that in some things, the innovation process increases the variance within 1 year. So you have the case that some years don't stochastically dominate first order. So I don't really see a reduction in variance, at least in this data. I didn't formally test for that, but this is by looking at all those graphs that I loved, but I took out because it's only a 20-minute presentation. But yeah, I have heard that about GE, that it's shrinking the variance, and that's the main thing. I didn't really see that it was shrinking the variance, but I definitely saw a lot of differing variance across years, which I would attribute that to also the genetic improvement process. They're trying stuff, they're throwing things against the wall, right? So, but yeah, so I had a little bit of that, but I haven't looked into it, I guess, as much as I could have. Any other questions?
Another factor you might want to look at is the level of the period is when those varieties are being developed, the environment, when those varieties are being developed, might be significantly different from the environment in those handful of years. And so the varieties are as well as they would have. You see what I'm saying?
Yeah, I think so.
When you're looking at why did that slow down, there could be another factor too. Because variety will develop under these environmental conditions. If you have 2 years of a slightly different environmental condition, then they might not seem like the yields much, but then you get different environmental condition and they start.
Yeah, I think you're pointing out genotype by environment, right? So in the fact that genetics developed under one environment, they're under a new environment during that period, so they're going to perform differently. Yeah, that's a really good point. And we'll have to look into more also because we have two yields here, right? We have private sector, but we also have these public sector varieties. And the improvement you're seeing is the gap between these, right? So if, for example, I think what happened with Jack is that Jack does really bad in 1 year compared to even Dwight. So then genetic improvement looks bigger in Jack. So that's also why, if I was looking, the point of comparison is probably better Dwight than Jack in terms of public varieties. Yeah. Yeah. That's a good point. So we should probably look in more depth. Yeah, exactly. Right. Yeah. That's right. Oh, that's a good point. Yeah. So I think what Scott's getting at is that if it's genotype by environment interactions, it should be really sensitive to our set of controls. And we don't actually see that it's sensitive to that. That doesn't protect us entirely from genotype by environment. But certainly with like sets of controls that you feel like might address that, it seems like it's robust to that. So.
those kind of factors, you're going to have to consistently
Right. Yeah.
differentiate impact the constant genetic public variety
Yes, exactly.
versus the constantly changing genetics
Yeah.
of the private
Right.
So any factors are differencing those every year. They're growing exactly the
Yeah.
same experimental conditions, the same
Right.
herbicides, the same seed treatments, the same
Yeah.
population, same location, same weather treatments.
Yeah.
So the difference in all those outcomes.
Right.
And
But it does leave those nonlinear impacts. I think that's what you're pointing out. And that was a bit of a wonky weather year too. It feels like that period. So it's worth exploring. So I think we'll probably just leave it at that. Do you want to go to the next speaker? Okay, thank you.
Second presenter is Dr. Lanier, professor at the University.
Yeah, so I always like to tell the impetus of why I do studies. And this one has a good story because I was drinking beer with some plant breeding buddies and they called me an idiot. And which is probably the impetus of all my academic work. Because we were talking about CRISPR, and in my mind, like CRISPR could solve the world. Like any problem we had, this technology is going to do it. And they basically called me an idiot. And the other impetus was I always wanted to get something published in Cell Press. Like, so I would always send articles to like Trends in Plant Science. And you know, when you send an email and you get the out of office response like 20 seconds later, that was like the rejection. Like I don't even think the editor read the whole title. So we got this published, and Job is the grad student on this, in iScience, which is like a 10 impact factor. And the reason I say that is because the amount of math in here is embarrassingly low. Like, I mean, this is like high school math. And so I always tell my grad students, it's not the math, you don't have to do mathematical gymnastics, it's just how you apply it. Yeah, so, and my co-authors are Hans Stuart Gent and then Aaron Shu and Wei at the University of Arkansas. So in my mind, you know, the famous economist, you know, they had this on their cover like 5 years ago. And like in my mind, this is CRISPR. I'm like, holy cow, I can reverse my male pattern baldness. Like we're going to feed the world. Like, and that's why my friends called me an idiot, right? Amongst other things. But that's what I thought CRISPR could do for agriculture. And they're like, you know, you need to talk to more plant scientists. And so that was really the impetus. Like instead of studies, which I've been guilty of as well, asking consumers if they would accept CRISPR, I never stopped and asked scientists like, well, what can CRISPR actually do in commercial agriculture? Because in my mind, this was all of our problems have been solved, right? So I do a lot of work in genetics, and the thing that really excited me about CRISPR was the fact that you can do things quicker. Right. And so in my mind, like you could be more adaptive to things. So a new disease hits or, you know, a new fungus. Well, suddenly you can cut your time from kind of initial cross to release in half, which, you know, I'm in Arkansas right now and we're going through a horrible drought. You know, just in my mind, you could pump out genetics much quicker. But I didn't know that. Like I read it, and it's funny, I've studied CRISPR for like 2 years now, and if you put a gun in my head, I couldn't tell you how it works. Like no idea. It's so, and I watch like YouTube videos for dummies on CRISPR, and I'm like, they lose me in the first 20 seconds. But so that really got me thinking, like, what do plant scientists think are going to be the big kind of benefactors of CRISPR, right? Instead of me asking a consumer about some hypothetical product that doesn't exist and would they eat it or not, like what can science actually do? And so that's kind of how we got started here. And you know, so the CRISPR literature is so deep in the hard science, but it's pretty sparse in the social science. And, you know, given climate change, and in my mind, like we could feed the world and pivot for climatic events, we really wanted to see, like, is this possible? Like, do the people doing this work think this can happen? Or is there just economists asking people if they would eat this if it was available? So, the literature, I try to combine kind of hard and soft science. So the literature is from hard sciences. There are a lot of articles about functions CRISPR could play in commercial ag. So that runs from like biofortification, and I do a lot of work in development, and I was super excited about biofortification, how it could help micronutrient deficiencies. And then we've got conventional kind of, well, not conventional, it's a bad term. We've got our traditional like transgenic stuff like herbicide tolerance and insect resistance. And then from the soft side of things, we've got barriers, like why aren't people or governments accepting? What could be possible barriers? And then what I was really interested in was what was like the impetus for hard scientists? Like how did they think this was going to help? Is it just yield increase? Is it profit increase? Is it, you know, the impetus trying to get more micronutrients? Is it food insecurity or environmental degradation? Right? I never stop and ask why people do the research they do. I just either marvel at it or reject it in a journal. And so I was really fascinated, like what was their motivation? Like, is this a pure profit thing, or did they think this could be more holistic for society? And there's the little CRISPR picture, which I have no idea what's going on, but I thought I'd put it up there because it looks nice. So, and again, the soft science is full of articles about people, would they eat it or not, or what government regulations might be in place, but there's not been like a holistic kind of collection of surveying plant scientists. So we developed a very, very simple survey, and we asked plant scientists what they thought the main functions would be, which crops could it be in, and then what areas of the world could be affected most. And then I do a lot of work on private-public sector kind of relationships, so kind of what you were doing, Jared. And I've always been fascinated about, you know, each of them peeing in their own corner, trying to own, you know, and would that be a problem in CRISPR? Because in my mind, I thought you needed some fancy lab and $50 million to do CRISPR research. And then like down the hall, a pathologist at Arkansas was doing it in like a tiny lab from like the 1950s. So I thought there shouldn't be this kind of huge divide between public and private sector, but I was curious about that. So my grad student, I'm sure most of us can appreciate this, he was like, we'll get 10,000 responses, right? Meanwhile, we're not paying anybody anything, right? This is like those emails you get like, hey, please take my survey. That was me, like, that was me. And so Yob was like, we'll get so many. And I'm like, if we get 50, I will jump over the moon. 50 is what I'm shooting for, right? But he put it on like his Twitter page as well. And I'm like, that's not gonna matter, right? Shockingly, we got 669 PhD responses, right? And I think the reason is we tried to sell it of like, hey, your opinion really matters, and we've never collectively put them together before. But when I saw that number, I was like, no way, that cannot be true. And actually we got 911 total because some breeders worked in the public and private sector, both. And so they took the survey twice. And like, I was so concerned that my master's student had fabricated these results. I went into Qualtrics and made sure that the unique identifier, the GPS, wasn't his apartment, right? Because I was afraid that he had filled them all out himself. But you can see it's a pretty representative sample. So we've got North America and Europe are dominating. It's not balanced, obviously. And the one thing I do regret, so Yob spent months scraping email addresses from universities all around the world. The hard part was private sectors. Like if you're a plant breeder at Monsanto, you're not just throwing your email address out on your website, right? So we didn't get nearly as many private breeders, but I was shocked. And I think the reason is that people answered these surveys is that I think they realized the importance of CRISPR, and you know, I think they saw the contribution they can make to this. And I'll show some of the comments that people put, because we were like, any general questions, man, hard scientists are not nice to the soft science. Like I'll show you some comments they put. So we just did, I mean, easy t-test, right? I mean, it's something you did in high school stats. So here's what we found. So the green means that it's significantly higher than the mean, and the red means it's significantly lower than the mean for any given category. So not surprisingly, fungus resistance and virus resistance across public and private and the different areas of the world were seen as probably the big vehicles for CRISPR. And that's not surprising because viruses and funguses or fungi are a global issue, right? You know, I thought, for me, just drought resistance, I guess in my idealistic world, like drought resistance would be the big one. But with the exception of Africa, that wasn't what they thought would be a realistic, and abiotic and biotic stresses are hard to breed for. And then in North America, herbicide resistance, probably just because of our high reliance already on herbicide resistance. So then the barriers, not surprisingly, like hard scientists were worried about consumers and what they thought, right? And then in my revise and resubmit, the one reviewer was like, look, I don't believe this. Like people are smart enough to realize the benefits this could provide. So I had to tactfully tell him, like, the general public are idiots, right? Like, you're very smart and work in a lab, but most people, even me, I can't tell you how this thing works. And so there's going to be blowback from it. So then policy and legal issues. So the same things that plague transgenics right now plague this. So this is the actual response I had to write to him. So I don't know if you guys have read, Brandon and Jason did a study about, they were convinced the American public had no idea what they were talking about. So they did a survey, and this is what they wrote. It said, this product contains DNA. The Surgeon General has determined that DNA is linked to a variety of diseases in both humans and animals. In some configurations, it's a risk for a factor for cancer and heart disease. This is the best one. Pregnant women are at very high risk of passing DNA to their children, right? 80% of the people Jason and Brandon surveyed said, if food has DNA, we need to label that it has DNA, right? And so that was my response to this hard scientist, like, man, you're changing the world, but the average person can't grasp, right? And like DNA, and like they even put DNA, right? If they had like just a generic thing, I'd be like, okay, maybe, but so then the benefits, or I'm sorry, skip that. So not surprisingly, most plant scientists thought the major benefits would be in the staple crops, right? Just because probably that's where acreage is and that's where the money's going. And then we have someone who was very mad that I didn't specifically ask if okra would be a main benefactor from CRISPR. Like you could tell people had dogs in this fight and they were going to bat for it. But I think for me, the interesting thing is almost universally, no one thought it would help with food insecurity. And maybe like the romantic in me was like the plant breeders that's what they're going to do, right? But then you can kind of see the confounding things because they thought it would increase yields, but not help food insecurity. And those things are correlated, not directly linked. And then what I also found interesting is, and this is where they just went off in the comments, they didn't want it regulated like transgenics. Like that, I got so many comments and like dossiers about how economists make policy and you can't regulate these things like transgenics. And then the private sector, they also thought the private sector would dominate, which is interesting because these are the people working in those sectors, and it was unbalanced towards the public sector. And it's a telling story, and I don't know why that they thought the private sector would dominate. So just in conclusion, like that was the math. Like I didn't even need to put a formula up there. I found this fascinating because it was like the first time, I think in the literature where people actually asked scientists what their research was going to do and not just assume that they could do it and then ask people if they'd eat it. The big takeaways were they thought the private sector would dominate, the staple crops, obviously, and then surprisingly to me, food insecurity and things like drought weren't prevalent in what they thought the main benefits would be. So I could have made 1,000 slides of this. So here are some comments that I got. This survey, it's surveys like this, which makes me glad that I'm in the hard science. These are actual comments that people wrote to me. Finally, an economist is doing something that matters. By the way this survey was worded, it's obvious you have no chemistry background, which is true. And the best, seriously, you need to go back and retake your PhD genetics courses, which that was a compliment because they actually thought that I must have had a PhD genetics course. There was like 1,000. I mean, the comments were hilarious. But yeah, so that's my presentation. I'd be glad to take questions or criticism or both. Yes.
How do you define plant scientists?
Yeah. So.
Plant scientists, you think they're camps in economics?
Yeah. No, for sure. So two things. So like we basically narrowed it down to pathology, plant breeding, entomology, kind of the standard definitions a university would give sectors. Yeah, so anything, and then we did a Web of Science search as well, trying to find names. That's how we got a lot of the private names, is a Web of Science search.
Is how much change there is in that community of scientists think as far as base motivation, which traditionally place of grass grow.
Yeah.
Doesn't appear that they've updated their.
Yeah, they're thinking, yeah, and it's, but if you worked with my dad's an engineer, so I need to be careful what I say. Hard scientists, I think, I mean, I always think that was the problem with Monsanto and GM. They come up with these great ideas and then they just think that the world's going to fall in love with it. And I think they're still stuck in that mantra to some sense of, I've always done it. It works great in a test plot, so therefore it's got to be great. And they're not pivoting probably as quick as they should. I think grant money probably does that, and checkoff funds really dictate a lot of their work, but.
Did you get a sense of what their intellectual property concerns are?
So yeah, so intellectual property was a concern specifically in North America, Europe, and Asia. And my hypothesis is that's probably where most of this research is being done. And they're worried about protecting that from how do you patent it, like things of that nature.
Did they just float across all the
No, interestingly, the public was more worried than the private sector. But again, our sample is not really represented. It's hard. I mean, I don't know how many plant scientists there are in the world, but to get 700 PhDs respond, like, and Job's like, oh, we need to do more surveys. I'm like, you need to stop here because you're never going to get this sample size again. You know, like it's, yeah. Well, thank you guys. Yes, I'm sorry.
So you with and maybe on your slide, you're more concerned with acceptance or policy.
Yeah, and so both, and it's hard to compare within. You kind of have to compare with the mean. They were more worried about policy regulation, right? Because I think in their mind, it's a great idea, so people will eventually accept it. But if a policy is written that prevents adoption, that's the real issue. Yeah, I don't know. We should have asked that, but when we were formulating this survey, like I didn't want to make it that narrow because I thought we'd get 5 responses instead of my hopeful 100 responses. But we just did this. I have another master's student. We just did something similar looking at the future of public and private breeding because I'm really fascinated in that. We got 2,000 responses. So I was much more poignant on asking kind of good questions like that in that one. Yes.
For all these years of hard scientists, for the decades, we've discovered work by economists with respect. Ask them what they think.
Yeah. But it's always weird because yeah, and it's funny because I always have to apologize when I go into a room. I'm like, oh, they're like, oh, here comes the economist. I'm like, so sorry guys, like, but I put a $ on what you do, and then all of a sudden we're best friends, and it's yeah, it's my mind doesn't think like that. But all right, well, thank you.
Okay, thank you for the great presentations. It was just, I really personally really enjoyed to learn from the other 2 professors before my presentation. So today what I wanted to talk about is the potential market and welfare effects of a gene-edited technology on the US soybean markets. I think that partly I'm going to talk about what already Dr. Hutchinson talks about. We're going to focus on the soybean market and also the CRISPR technology, which is, I feel like, really fascinating and which is adopted in agricultural production. My name is Yoon-Kyung Lee. I'm originally from South Korea. I am currently as a visiting assistant professor at Doane University, and I just completed my PhD at the University of Nebraska-Lincoln. So I wanted to briefly start with why we think that there's a potential market for genetically edited crops in the United States. Well, gene-edited high oleic soybean is the first crop that is commercialized in 2019 in the United States. I still remember that why I start wanting to like research about this topic, just like Dr. Hutchins, the Dr. Lanier. I was read about the like news articles about how the CRISPR or Talon's technology, which doesn't really requires for the using the foreign DNA to change the crop traits. And I was looking for the what kind of crops or the fruits and vegetables that is actually commercialized in the United States. I found that the high oleic soybean is the first crop that is commercialized in the United States. Currently, this new varieties is available in a few states in the United States, just only 13 states in few cities, because there's not much accessibility of these new types of crops. I wanted to talk about why the bioseed companies is focused on like put a lot of pause for producing this new types of variety. And I wanted to talk about the trans-Tibet regulation that is discussed for a long time since 2009. In terms of the processed foods. So you might wonder that why this is relevant, that this trans-Tibet regulation actually requires for the food processors to utilize some healthy, the high oleic level of oils instead of use of any low oleic types of oils that requires a partially hydrogenation process. Well, the reasons that food processors need to use this partially hydrogenation process is because they wanted to utilize something the oils has a higher functionality and the greater flavor, so that they could utilize those types of like oils, like change the types of oil from the liquid types of low oleic oils to the thicker types of the low oleic oils in the room temperatures, so that the food processors utilize these oils in the long term with a better function. So we think that this is kind of food innovation in the market once this high oleic soybean oils and also the high oleic types of soybean seed is adopted by the farmer successfully, and these new types of oils will be available in the US market, then this will be the substitute of any types of low oleic vegetable oils such as corn, or soybean oils, or even other the oils that requires a partially hydrogenation process, so that will gonna give you another choice for the food processors in the market. Well, these types of new soybean seed, you could think that what is the high oleic soybean, and you could imagine about like the better functionality as well as the better health benefits. This high oleic soybean oils has a very similar fatty acid compositions, just like olive oil. So you can imagine that you might heard about these types of like olive oil that actually reduces the cholesterol levels. And also there's some studies that reduces lots of the health risk of having a cardiovascular disease in the long term. So in that sense, these high oleic soybean oils actually can give the benefits, the health benefits for the consumers, and also have a benefit for the food processors to avoid this trans-fat regulation in the market. So as a farmers, they're going to expect some price premium once they adopt this new technology. So the major objective of this study is we wanted to analyze the market response to the introduction of these new types of high oleic soybean seed, and also that we wanted to capture that who will gonna gain and loss in terms of the supply chain who are involved in this the new technological development in the soybean supply chain, especially for consumers, processors, and farmers in the United States. As you might expect it, there are not many data available in this market, so we decide to utilize a simulation to quantify the market and welfare impacts of the agents who are involved in this technology. So again, we're going to consider the bioseed companies and also the soybean farmers and soybean processors and consumers. And I wanted to stress out that the 80%, more than 80% of this high oleic or low oleic types of soybean oil consumers is food manufacturers or the US food processors, and less than 20% will gonna be just household or restaurants who are gonna use this oils as cooking oils. So in terms of the theoretical framework, I wanted to kind of differentiate between, explain a little bit more about the inputs and outputs we include in the cost functions. That's going to be explained in the next slides. We separate with the farmer sector and processing sector. And we define that inputs for farmers will gonna be two types of different seed, both the high oleic soybean seed and low oleic soybean seed. And we consider the other inputs such as land, fertilizers, and labors. And the outputs will gonna be both high oleic soybean and the low oleic soybean. And also we consider corn, as you might know that like the corn and soybeans has a benefit for farmers to rotating between two. So we consider the corn as also the output. For the processing sectors, those outputs, farmers' outputs will gonna be utilized by the processing sectors, and also they will gonna produce the output, the high oleic soybean oil or low oleic soybean oil, and the soy meal, which is a byproduct of the soybean oil. So we utilize a pretty simple equilibrium displacement model that is introduced by Muth and elaborated Dr. Perrin. And we considered set up the two different cost functions, which is represented by C, and with the superscript F represent the farmers and P represents the processors. So basically these cost functions define that they were going to try to minimize the input uses that is represented by the lowercase x, and to produce the output level, which is Y. And given that there's an input price, which is represented by the W. And we introduced the small letter, the lowercase letter of the T in the soybean farmers to introduce like there's a technology will gonna be adopted by the farmers, not the processor sector. So we try to link these three different sectors, and we set up the matrices. We utilize the comparative statistics and set up the matrices to figure it out, what would be the market and welfare impacts of these new technological introductions. The major benefit of using this model is that we could separate the endogenous parameters on the left-hand side and efficiently introduce the exogenous parameters separately. As you can see that there is a gamma and RH and the M as the exogenous, the output shocks. So I wanted to a little bit talk about a little more about those exogenous shocks. This gamma captures the production cost change with respect to technology. Before I actually introducing, looking for some numerical values for this, the production cost change for the farmers, once they try to adopt this new variety, I expect that the production cost will gonna be changed, because I saw there are so many papers talks about CRISPR tolerance technology is cost effective. However, what we found, what we estimated, eventually found is that actually farmers who are going to adopt this new technology at this point, they need to pay more because of the two reasons. The first is that they need to put up with the segregations cost. They need to segregate, differentiate between the conventional, like genetically modified soybean and the new types of high oleic soybean. And as well as there is a lack of traits, especially for the gene-edited high oleic soybean, which doesn't have a traits for the higher yields, so that they actually farmers need to pay more production costs, which is almost 11%, to adopt this new technology. Even lots of companies try to give an incentive for like the farmers who willing to adopt this new technology. Still those are, could be partly mitigated, but still those are the costs will be relevant with this new technology. So we introduce as exogenous shocks. In RH that captures the input supply shock, there's companies that try to expand their accessibility of these new types of soybean in the US market. So we're going to introduce that input supply shocks. And the M captures the output demand shocks, as we talked in the first slide that there's a food policy effective since 2021 in January. And because there's a substitution effect between high oleic, the new types of soybean oils, and the low oleic, the genetically modified, which is the conventional soybean oil. So we captures and also introduce that as the exogenous output demand shock in the model. So these are the first result that look at the changes in pricing quantity in terms of the relevant market. So when you look at this second column, this shows that when the supply shocks is only introduced in the market. And this third column captures when the both demand and supply shocks introduced in the market. Well, for the supply shocks, we introduced the 50% decrease in the price of high oleic soybean seed that captures the greater accessibility of the high oleic soybean seed in the market. And we used the 10.7% of increase in marginal cost for producing these new types of soybean, especially for the farmers. And for the demand and supply shocks, we introduced the lower limit scenario and upper limit scenario. The upper limit scenario is more like positive scenario. We expect that there's a greater magnitude change in terms of price and quantities. And this lower limit scenario is basically we got the numerical values and estimated change in terms of demand for high oleic oils and decrease in low oleic soybean oils based on the private conversation with the checkup. Normally based on the data from the future contracted acreages for the high oleic soybean seeds. So the reason we kind of separate these two different shocks is because we wanted to see that, so if the bioseed companies and farmers to be successfully adopt these new varieties, that what is the major factor that actually drive change in the market equilibrium at the end. And as you can see that when we introduce the supply shocks, those pricing quantity changes are pretty much insignificant. Whereas when we introduce both demand and supply shocks, we could find that the magnitude of change of the pricing quantities way greater than before. So when we look at the specific data, you can see that when the both demand and shocks are introduced as a lower limit scenario, we found that the high oleic oil prices increased by 62.3%, and the market, the quantities increased by the 157.6% under the demand and supply shocks. You might think that these are something, the number is kind of exaggerated, but we expect that kind of numbers. The reason is that normally the high oleic oils, the price, such as the olive oils, when you think about the price differences between such as the corn oils or low oleic vegetable like soybean oils and also olive oils, the olive oils price is even triple expensive than those types of like low oleic oils. So that the price change is kind of reasonable and what we expected. And even quantity, we assume that initial market share for this high oleic soybean is just 5%. So when we consider those like 157% increase in terms of the market equilibrium, still it just accounts for like increase in terms of market share for high oleic soybean oils from 5% to 12% approximately. So these are the results about the welfare changes. So what we found is that the major beneficiaries for this new introduction of the adopting this new technology will be the soybean farmers, who are going to get benefit by the $1.43 billion in the upper limit scenario, and followed by consumers who are going to get like $286.4 million. And what also find is that the soybean processors, input suppliers, and the soybean seed suppliers will going to be lose their benefits. Under these scenarios, under both the demand and supply shocks introduced scenarios. So 3 conclusions what I found from this study. The first is that the welfare benefits is biased towards the soybean processors and also the high oleic soybean oil consumers when this new technology is adopted. And also, as you remember that we talk about the table to differences between the supply shocks and demand supply shocks. Based on that, what we expected is that even the bioseed companies try to increase the great accessibility of these new types of varieties and also increase some of the programs for the farmers. The major factor actually drives increase the price and quantity and change the welfares will gonna be depend on the consumer valuation of these high oleic soybean oil attributes. So currently the soybean, the food processors, they are using sometimes the medium oleic level of oils such as palm oils, or maybe they are using some specific types of high oleic oils, which is canola oils. I believe that the success of new types of varieties, we're going to need to talk about there's a lot of health benefits for using these new types of soybean oils, as well as the environmental benefits for using these new types of varieties. So that's all what I prepared, and I would happy to accept any questions and love to answer the questions as well. Thank you.
So net welfare is positive or negative? I'm trying to add them up.
Mm-hmm.
Like, does the surplus that the producers gain and consumers gain outweigh how much the soybean?
So I didn't really calculate the whole changes in terms of the welfare. But when you just consider about the soybean farmers and the higher like soybean oil consumers, the benefit that is actually, when you add them up, that actually outweigh the other sectors of the loss of the welfare. So I think that the net benefit eventually will gonna be positive. And these are basically in terms of the lower limit scenarios, as you can see that it might be not. I didn't really have a chance to calculate the whole net welfare, but yeah, that's great. Yeah. Any other questions you have? Okay, thank you very much.
Very consistent theme of this session.
Right.